Hi, I am Nico Zervas and I'm the CEO for CAT. Thank you for joining our webinar on ultra-low latency TSN networks. I hope this would be time well spent for everyone. So in the beginning, we're going to give you a sort of introduction to TSN protocols and profiles. And we would later dive into the topic of the webinar, which is latency sources and ways to optimize latency. I would like to first go through short introductions. So as I told you, I'm the CEO for CAST. CAST has been around since 1993. We do IP cores since 1996. We are one of the older IP vendors out there. We have headquarters in New Jersey. We have offices in North America and Europe. Over the years, we have helped more than 2,000 customers, 8 billion of products. And we've done that by providing excellent products and superior support. So all we do is IP cores. We develop them. We market, license, and support IP cores. We extend our offering with qualified products by select partners. One such partner for the last 20 years has been Fraunhofer IPMS. And I have the pleasure to have with me today Marcus Teets, who's the group leader for IP cores and design services at Fraunhofer IPMS. Marcus, please.
Hello, everyone. Also from my side. So as Nikos already introduced me a bit, I'm with Fraunhofer. We were teaming up with CAST quite a while ago, and for those of you who never met Fraunhofer before, so we're a European innovation powerhouse, and we're a non-profit organization doing applied research to the benefit of the society, and our vision behind that is bringing ideas from the academic sector to the market. So here we deal with FPGA design, support our customers here, as well as in silicon ASIC design, and also we're adding software integration and software transmission up into the cloud. So basically what we're going to talk about today is TSN, time-sensitive networking, which is not a single standard. TSN consists of multiple standards and extensions and profiles, as Nikos already mentioned before. It evolved from the AVB task group in 2012. The AVB task group was focusing on latency-free delivery of audio and video data, and from that task group, the TSN task group separated. So as mentioned before, TSN is not a single standard. It's more or less a collection of substandards and extensions, which are focusing on network-wide time synchronization, as well as determinism in data transport, as well as low latency and low jitter. So, and as TSN is working on top of the classic Ethernet standards, it scales with the speed and with the evolution of Ethernet. So what's the vision behind TSN? So one of the visions is that TSN, time-sensitive networking, is enabling the merge between IT and operational technology. It can avoid the use of proprietary and incompatible solutions like widely used field buses. And it is focusing on interoperability and scalability of networks. So I just listed some of the standards in this slide. So as you can see, one can cluster the standards a bit. So some standards like the 802.1 AS and its profile IEEE 1588 focus on time synchronization, which can be seen as kind of a basement for the TSN standards. So often TSN applications make use of time synchronization. Another cluster is the standards focusing on bounded low latency, focusing on reliability. And on top of these standards, there are additions focusing on resources and API, searching for solutions for configuring networks and so on. So, and to ease a bit the use of TSN, recently there is a strong push for the definition of profiles, of TSN profiles, focusing, for example, on audio-video bridging, front haul application, or industrial automation, automotive communication, and the latest of these profiles is now aiming for airborne use of TSN. So with that being said, I want to step through some of the most important TSN standards used nowadays just to get everyone on the same level of understanding before we start deep diving on the latency topic for today. So as already mentioned, most TSN applications make use of the time synchronization according to 802.1 AS or its revision AS 2020. So the time synchronization is focusing on network-wide operation. It's aiming for network-wide time synchronization. And if the AS standard is used as required by the standard, non-AS capable devices would break up the network. So there are some ways of dealing with this drawback, but I will keep them aside for today. So the synchronization, the network-wide time synchronizations usually is started by periodic announced messages, and then a grandmaster select algorithm called BMCA would select the device with the best accuracy in regards of clock precision. And this device from there on will serve as a grandmaster for the network. And all the slave devices would synchronize to the grandmaster clock provided. So once a synchronization was established, periodic synchronization and follow-up frames will keep the synchronization up and apply corrections to the synchronization where needed. The AS standard is based on a peer-to-peer measurement of path delays. So it can be seen of like measuring the delays packet need to be transported between two communication partners, and based on this information, the whole synchronization of the network is set up. Then there are standards for shaping traffic in terms of bandwidth allocation or traffic timing. So first of all, to mention here is the 802.1 QAV, the so-called credit-based shaper, which was already used by the AVB task group back then. It is operating in a credit-based way, which means each data stream would have its own credit, which is decreasing by sending frames and increasing in times when there's no traffic being sent. So, and if a data stream would have negative credit applied, it would not be allowed to send traffic for that period of time. So this gives you the opportunity to set up bandwidth per stream in the network. The next shaper, which can be seen on top of the AS time synchronization, which is making use of AS time synchronization is the 802.1 QBV time-aware shaper. So the basic idea behind that is to make use of the network-wide time synchronization and to define repeating cycles within on a timeline. And there one can define a number of gate operations where one would open the gates for certain traffic classes and block the channel for others. So with that, you can reliably define time slots when different streams might send data on a channel. Another standard I just want to briefly mention here is the frame preemption, which is a mix of two standards actually. It's focusing on extreme low latency data transport for chosen traffic classes, which we call express traffic. So how does it work? In the image on the left side, you can see a data transport without frame preemption enabled. So if a low priority packet is already on the line and there would be express traffic showing up, the usual way is that the low priority data frame would be transferred, and afterwards the express frames would be transferred, which gives you a huge amount of latency in the worst case situation. If you switch on the frame preemption, this would allow express traffic to interfere the data transport of low priority background traffic, and which would result in fragmenting the low priority background traffic with the benefit of ultra low latency processing of express frames. Another standard I want to briefly mention is the reliability standard 802.1 CB, which is called the frame replication and elimination for redundancy. This standard gives you the opportunity to split data streams and transfer them using separate physical channels and reunite these data streams on the receiver side. The last standard I want to shortly mention here is the QCI, per stream filtering and policing standard, which is giving you the opportunity to, let's say, identify the bubbling idiot in the network, which would enable the possibility on checking if certain traffic is currently allowed to be sent. So you would set up using this stream this standard gates where traffic can only pass in certain frames of time, and if they don't, they will get terminated and an error would get raised. So about TSN, CAST and Fraunhofer IPMS. So there are several TSN enabled IP cores which we offer. So first to mention, there's the TSN endpoint core, which is basically used as a network endpoint with TSN capability. And the next on the list is the TSN switched endpoint, which is enabling daisy chain applications or even ring topology, also the like. The more complex solution, the TSN switch, can be seen over here, which is an infrastructure component, which is a TSN enabled switch IP core with optional host port functionality. And then we also offer a CAN to TSN gateway, which is enabling bridging between TSN and CAN networks. So all these IP cores have extensive standard support for TSN standards. They are target independent, which means they can be used for FPGA designs for any FPGA vendors, or they can be used for ASIC implementations as well. We focused during development on small footprint and cut through and store and forward possibility. All these cores offer high synchronization accuracy based on 802.1 AS. They come with extensive software support, and they support stream-based data handling as well as packet-based data handling. They hereby be used with CPUs. And what we optimize these core for is very low and configurable forward latency. And this is the starting point where we start our deep dive on investigating about latency today. So we first of all need to define our common sense of latency. What are we talking about here? So if we are talking about latency, usually we mean the time data packages need to be transmitted through the network from the source towards the sink. In some applications, this is just a single path transmission, and for some use cases, you would speak of round trip latency, where you would pass on packets from this source to a remote device and back to the source. So for investigating on latency, let's put a kind of example network in place. So let's assume we have this more or less complex network, which we can see now, and let's assume we want to forward data from the TSN switched endpoint on the left side, doing 2 hops over TSN switches and push on the data packets toward the sink, which is in this case a TSN endpoint on the right side. But there are also crosstalkers. So in that case, we would have this switched endpoint, which would have switched on the .1 CB functionality and transporting its data over separate physical links towards this switched endpoint, which we can see in the lower end here. And of course, we have more traffic in the network. That endpoint wants to transfer traffic data packets to this endpoint, and you can imagine more of these data streams within the network. So what we want to focus on is how to optimize the latency for this certain data path. So we will stick with this example, with this data path for now, and to investigate on latency sources along the path, we set up this setting within the laboratory where we have a FPGA based TSN endpoint on the left side, 2 TSN switches in between, and 1 TSN endpoint as a data sink. Additionally, we introduced 2 tablet PCs, which can generate cross traffic on this network. So how would our latency path look like from the data source towards the data sink? So we will have this endpoint, which would give us some ingress latency, and then there would be a phi involved, some kind of cable delay, another phi. Then we would need to jump over this switch, then again cable and phi delay, another switch, again phi and cables, and then we would see some egress latency as well on the endpoint and on our sink. So first of all, let's investigate on the phis and cables a bit. So let's do an assumption here. So there are physical limits which apply here. So if we talk about copper networks, which we are investigating today, we need to take into account 5 nanoseconds per meter of copper cable involved. Then, of course, we have phis in the network, which will give us additional delay. So we are using this micro phi in this example, where you can't find data sheets which would pinpoint the latencies to be expected here. But we found a a pretty similar PHY where the data sheet would give us some rough estimation on the delays which we would need to expect here. And then we would also have to take into account some PCB related latencies, and as well as magnetics would introduce some delays which we don't know yet. So just to sum this up, as a first guess, we would expect around about 500 nanoseconds with the cables we're using here and the PHYs. So just to see if this matches the reality, we set up this measurement in the lab. So we set up an oscilloscope and are scoping the RGMI TX enable signal towards the PHY, and on the opposite side we are scoping the RGMI RxDV signal to see actually when the packets made it through the cable section. So well, let's see what's happening here. So you can see our setup in the laboratory, and you can see the packets entering in the red scope, and you see this is giving us a latency of 555 nanoseconds for the data to pass through the PHY, the cable, and back again through the PHY. So this is a bit more than we expected, but it's in the same region. So just remember this for now, 555 nanoseconds. We need to pass the cable and the PHYs. So now let's move on. So let's investigate a bit on the delay which the endpoints would introduce to the data path. So we will see some egress delay for the first TSN endpoint, and we of course will see some ingress delay on the remote side. This, of course, strongly depends on the shaper configurations, or if you switch on or off frame preemption for those endpoints. And of course, this would leave you with some additional software delay. So let's see how which delays one would need to expect here. So on the egress side, so one could opt for having a Linux-based software utilizing DMA transfers to push the actual data packets from the memory of the system towards the endpoint. From the literature, one could assume to have delays within the millisecond range here when using standard Linux kernels. But one could also opt for having a delay optimized RT Linux kernel, which one would assume to leave you with sub-milliseconds latencies. If there is the need for less delay, there's also the option to opt for RTOS software-wise. So in this case, we just put a example using FreeRTOS, which will give you the opportunity to highly optimize the timing within the software system, and one would expect to reach delays and jitters within the microsecond range when using a RTOS-based software system together with DMA transfers and TSN endpoint core. The least latency you can get from utilizing a TSN endpoint would, of course, to rule out any software related delay and to just push on data streams towards the endpoint, which would completely kill all the software latencies. On the receiver side, it's the opposite way around. Again, you would have to do some DMA transfers for the software, and then the data packets would need to make their way through the software stacks. And in the case you would use the endpoint core with additional third-party IP or any other stream processing units, you would not gain any software latencies. So what does this mean in real life? So let's investigate a bit on that. So we got this TSN endpoint set up on the FPGA you have seen before. We are using a non-RT Linux 5.10 kernel, and the software is running on a ARM Cortex A9 core. So in this case, we're triggering external ports on the actual socket send function. And again, we're scoping the RGMI ITX enable signals to see when the packets actually pass on towards the PHY. And on the opposite side, the opposite way around, we again scope the RGMI RxDV signals, and we will toggle and port once from the user space of the Linux software, the data packet will get recognized. So let's see what the actual software latency will be like. So we are again seeing the setup from the laboratory, and if we zoom in on the signal, you see that we are dealing with a egress delay of 33 microseconds and a bit more than 60 microseconds on the receiver side. So this is something to be taken into account when we are talking on latency. So what's to mention on the software side? So we were seeing a less latency than we were expecting for Linux systems. This example is the case because of we had a very light utilization scenario for the Linux software, so we are not having extensive background tasks to be processed by the Linux kernel. So let's see how we can improve the situation by using an RTOS. In this example, again, we are running the TSN endpoint on the FPGA, on the very same FPGA. Again, we are utilizing Cortex A9 core, but this time we are running a free RTOS, which is the case for the sender as well as the receiver side. And again, we are toggling ports on socket send operation as well as socket receive operation. So let's see what's happening here. Again, we can see our setup, which is pretty much the same from the laboratory, but already from this perspective, one can see that we're down with the latencies. So as we can optimize the software on utilizing this RTOS way better than we can do on Linux, we are left with just 4.4 microseconds on the egress side, as well as a bit more than 15 microseconds on the receiver side. So, but what is the best we can achieve in terms of latency for highly demanding applications, for highly demanding use cases? So we again are running our TSN endpoints on the endpoint on the very same FPGA we did before, but this time we are using an HDL-based packet generator to inject data packets into the TSN endpoint core, and on the opposite side around, we will have a stream receiver for receiving the data packets. So again, we set up our measurement equipment in the lab, but this time we are triggering on the AXI valid signal for the AXI stream being forwarded to the TSN endpoint. And again, we're scoping our RTMI TX-enabled signal to see when the data packets are done being pushed through the endpoint. And on the opposite side, we're scoping the RxDV signal, and again, are looking on the AXI valid of the AXI data stream we get presented by the endpoint. So let's go to the lab and see what is the lowest latency we can achieve. From this perspective, you already can see we needed to change change the resolution of the oscilloscope. So in this case, we're down to 168 nanoseconds for TX and 288 nanoseconds for RX operation. So this is the lowest you can get by using the endpoint on this specific FPGA and present the data present the data by just streams. So now that we know our egress delay and our cable delay for the data source as well as the data sink, let's investigate on the forward latencies our TSN switches would add up to the data path. So first of all, we need to figure out which mode of operation is used for these switches involved here. So there are two best possibilities. These switches can be operated in a store and forward mode, which would mean they would wait until a full packet did arrive before pushing on these packets on the transmission line. And the second option is using the cut-through mode, where the data would not need to be stored within the switches and is just being pushed on as fast as possible. Of course, as we're in this example are focusing on ultra low latency, we are using a cut-through mode here. So again, we are running our laboratory example, but this time we are scoping the RGMI signal towards the TSN switch, and on the opposite side we're scoping the RGMI TX enabled signal to see when to measure the time actually the packets need to be processed through the TSN switch. So let's again go to the laboratory and see what we can get here. We see the familiar setup in the laboratory, but this time we are just scoping on the switch and the time it needs to process the data. So we see we're down or we are faced with forward latencies of less than 1 microsecond here. So the data sheet actually states this latency of a bit less than 1 microsecond. You might wonder why we were seeing less delay in that case. This was due to the fact that we were using an experimental switch, which was not released yet, but this one is optimized for even lower latencies. So now let's talk about cross traffic. So let's assume the data path between the two switches would need to be shared with additional traffic. This would result in indeterministic jitter for our data packets, which we want to send along the red path here. So let's do some basic calculations on what to expect here jitter-wise and latency-wise. So let's assume we are dealing with a 1 gigabit per second data rate here. And in this example, or with this given, a data frame of 1.5 kilobytes would already take 12 dot something microseconds to be just passed through the network. Frames of the size of 64 bytes would still take more than half a microseconds to be passed on through the network. So this, of course, rules out the use of store and forward operation for ultra-low latency data streams. And again, this is underlining the need for having a cut-through operation IP to be used for highly optimized for highly optimized low latency data streams. So all of our IP can handle cut-through operation, and of course, for this example, we use cut-through operation. So, which possibilities one has to optimize the forward latency for data being processed through these two switches and the line in between. So the first option would be to set all the traffic lights to green for the data packets to be passed on, and to define and implement a strict timing regime based on 802.1 network-wide time synchronization and the QBV scheduler. There's another option, and this is the option to use the frame preemption feature and to define our prioritized data as express traffic and to merge this traffic into the background traffic packets. So let's investigate a bit on the critical path if we are opting for the strict timing regime. So as mentioned before, one would utilize the 802.1 AS time synchronization, and on top of that, one would use the QBV schedulers of the TSN capable devices to open all the gates at the moment to make sure all the gates are open when data needs to be transferred. But this comes with two assumptions. One would exactly need to know when packets would need to be delivered. And one, of course, would need to know the maximum size of these packets to reserve the time slots to this traffic class I want to process through the network. So let's do some calculations here. We know the egress delay of our endpoint, and we know the delay to be expected through the PHYs and cables involved, and we do know the delay involved, the delay introduced by the switches, and we know the ingress delay to our data sync. We can do a worst case data path calculation, which would result in 4.9 microseconds, excluding the software latency we were investigating beforehand. So the second option would be making use of the frame preemption feature of these switches. So this does rule out the need for network-wide time synchronization, but of course one could have time synchronization implemented, and also you could use the QBV time-aware shapers or the QAV shapers on top of that. Here there no need to exactly know when the data packets would need to be transmitted, and I don't need to know the maximum size of these packets. So I would just configure all the other traffic in the network as a background traffic, and I would configure our highly time critical data traffic to be processed as express traffic. So let's do the calculations here. Again, we see the ingress and egress delays. We see the cable delays. We see the delays introduced by the switches. And on top of that, we now see additional frame preemption delay. This comes from the definition of the minimum frame size, which could be used by a frame preemption feature, which is defining a minimum frame size of 64 bytes. And this is exactly the time, the worst case time I would need if a background traffic packet is already being processed by these switches. They would have the need to wait until these 64 bytes are processed, and then the express traffic can be merged into the data stream. So let's investigate a bit using our laboratory based setup again. So we again make use of our well-known FreeRTOS example, which we already measured on. So again, we are scoping on the socket send signals, and we also will see the RGMII signals on the sender side as well as on the receiver side. But this time we will have the possibility to inject cross traffic on these switches, and this cross traffic would also need to be transferred from one switch to the other. So let's see what happens here. So again, in our laboratory, you can see the familiar setup, but this time we use the tablet PCs to do a iPerf measurement and to inject huge amounts of traffic to the network. So now we see everything is fine, but once we switch on the cross traffic, we will see indeterministic jitter and more latency for our critical data. So and now I can go and switch on the frame preemption feature, and we will see this will leave us again with reliable forward latency, and this will reduce the jitter. It is not completely reducing the jitter, but this was what we were expecting here. You can still see the 65 byte jitter of the interfered packets. So with that insight, we would like to round up this session for today, and I would like to hand over to Nikos to introduce the Q&A session and a short poll here.
Marcus, let me see if I got it right. What I think I've learned today is that end-to-end latencies in the order of few microseconds are actually feasible with TSN networks and not just point-to-point connections. And in order to achieve something like that, you basically need to do three things. One is to carefully analyze your traffic so that you can come up with these QBV schedules or to make sure that preemption would actually work. The second thing is that you need to use cut-through switching throughout your network, very important. And the third thing you need to do is you need to use custom hardware, optimized endpoint and switches with minimal software in the data path. And with that, you can actually go and develop networks with very, very small latency. And the best way to do that, of course, is to start by building your networks using IP cores from developed by IPMS and available from CAS. Now, I see we already have a few questions. So the first one, Marcus, is what are the latency requirements in different applications, i.e., automotive, industrial automation, etc.
Thank you, Nikos. That's a good question. So we see different latency requirements here. So a strong driver for ultra low latency currently is the ADAS applications we see in the automotive market, where you see LiDAR applications and stuff like that, or from the industrial sector or the medical sector, you see applications like tactile applications or closed loop application, which have strong focus on low latency. But within these sectors, there's also applications which doesn't come with these highly demands on latency.
Thank you, Marcus. So the next one here, what is the extra latency a real-life software application would introduce on a Linux or real-time operating system?
That's also a good one. I investigated a bit on that, or I mentioned that a bit during my presentation already. So as, for example, we use standard Linux kernel without any background load. So if you just would put huge background load onto this system, of course, your latency and more important, your jitter would raise towards the milliseconds range. Of course, with RT kernels or RTOS-based software applications, this can be cut down. Software latency definitely is something which one would need to consider. So on Linux, you would have to deal with delays of milliseconds, or if I opt for a RT Linux kernel, this would leave me with a latency in the microsecond range. And with RTOS, you could achieve latencies of less than 50 microseconds.
So we have some more. Have you also investigated the impact of packet jitter and wonder on the accuracy of PTP?
Did I get it right? So you're talking about how the PTP accuracy would interfere or would influence the forward latency and jitter, right?
Yes, I think that's the question.
Okay. So, okay. Yeah, of course, as the synchronization in network-wide synchronization would be the baseline for configuring my QPV schedulers, if I would use those, the synchronization accuracy would, in the first hand, be responsible in terms of jitter I can handle. So I need to have a very high quality network synchronization accuracy also over time to keep to maintain my low latency and low jitter within the network, of course. So this has to be taken into account. The high accurate network-wide time synchronization is the base for having this ultra low jitter.
So 5G is expected to become a means of communication in Industry 4.0. Do you plan to investigate TSN over wireless?
Yes, sure. So let's speak Fraunhofer here. So we're already investigating on that heavily. So in our business field, for example, we are dealing with Li-Fi communication, where we are currently strongly focusing on bringing TSN to Li-Fi network. We're as well dealing with projects focusing on RF applications utilizing TSN. So yes, and as we can already see from the profiles which are currently evolving, 5G is also a topic here.
Okay. Can cut-through be used for mixed speed environments too? For example, 100 megabits link to a switch and then 1 gigabit per second between switches and then again 100 megabits to forward to the endpoint.
And that's a good one. So in principle, yes, but it comes with, of course, with some restrictions. So if I, for example, present the data using a 100 megabit link towards a hub where I would have 1 gigabit, I can of course use cut through in a limited way. So I could I would need to make the background traffic wait a bit longer for the packets to arrive. But this can be done, but one would have to make his calculations. So in principle, yes. Let me answer it that way.
So we have one more. Would you expect virtual switches to ever become an option for TSN in industry automation?
Yeah, difficult one. Yes, of course, one can do also can do virtualization here. But again, one would need to figure out the use case in the first hand. So what are you planning to achieve? If we stick with our example for today, virtualization, of course, would introduce additional jitter or latency at these or that point. So yeah, it's difficult to answer it overall. So yes, it is an option. It could be an option, but it's strongly depending on the use case you're aiming at.
One more question. So, do you expect cut-through to be standardized? Uh, I don't know how that could be things that relate to the actual hardware architecture, but I guess there could be some provisions. I don't know. What's your take, Marcus?
There are discussions ongoing on that, but it's difficult to address. Yeah, there's discussion ongoing, so maybe this will result in some kind of standardization. So we will have to see. It's not that far that I would say we would expect this within the next year.
So with that, I would like to thank you all for your time. If you want to learn more about our course, please visit our website, drop us an email, or call us. Our details are on the slide. You can find more information at www.cash-sync.com. Thank you again.